Here they have given a potential curve and they are asking the probability distribution. First let us assume this is the particle's energy. Let us say this is E and this is region 1 and this is region 2, and this will give you the kinetic energy, and this K1 in the first region is given by under root 2m E minus V by h cross square, and this difference will give you kinetic energy in this region, and we can write in the second region K2, this is under root 2m E minus V by h cross square, and this value is more than this. And if you observe one more thing, here this region we are having a more attractive potential. So see, this depth is more compared to this. This is more attractive potential, more attractive potential. Okay, so and this region, first region, this is a less attractive region, less attractive region or potential. Okay, so whenever a particle is moving in a more attractive potential, there we will find the particle with more probability. That means a probability of finding the particle, finding the particle is more when compared to this region. So in the second region we must have more probability compared to the first region. So that's why the answer is 1. Or else we can do in another way also. Let us consider like this. Now we have already defined this is the energy of the particle, and this will give you the k value in this region, which is already we have written K1 is equal to under root 2m E minus V by h cross square, and in this region this will give you the K2, already we have written there, under root 2m E minus V by h cross square. If you observe carefully, this K2 is greater than K1. Second region K2 is greater than a first region K1. So what is the relation between lambda and K? Lambda is inversely proportional to K. So this implies lambda 2 is less than lambda 1. So we can say here in the second region we have less spreading. We can say this is a less spread, and here we can say this is more spreading, because the kinetic energy is here it is more than in the second region kinetic energy is more than the kinetic energy in the first region. So that's why we can say the probability of finding the particle is more in the second region. So this problem is also quite similar to the earlier one. They have given this potential and they are asking the probability distribution curve. Okay, let us take this is the energy of the particle, and let us say this is the first region and second region. It's very clear, and here this will give you the k value, let us say K1, and this will give you the K2, second region. But second region is also second region, first region, both are having some negative potential, but of course this is more attractive potential. Second region contains more attractive potential compared to the first region, and this first one is having less attractive. So wherever the region in which we have the more attractive potential, here the probability is more, and here the probability is less. So we can conclude that in the second region we have more probability compared to the first. So I think this is the answer, third one. in this question they have given some potential regions. So this is the x, and here we have potential, and this is the step potential. This is the region 1 and this is the region 2, and here the particle is incidenting with this energy. Okay, so in this region the potential is given, that is V naught, and this is the region 1. What is the potential here? 0. And in the region 2, what is the potential? V naught. So whenever 0 potential is there, the particle is free. If the particle is free, the solution is what? Sinusoidal. The solution is a sinusoidal. And here the potential is V naught, but energy of the particle is less than V naught. Whenever energy of the particle is less than V naught, then the solution, the psi, is exponential. But again, exponential means you will be having a growth and a decay, but this is a right side. That means as x tends to infinity, positive plus infinity, the valid function is a e raised to minus kx. That means this is a decay. So here this is decaying. This is decaying, and here it is first region it is sinusoidal and second region is decaying. In this question they have given again the potential regions are given. So this is the potential, step potential x, and this is v of x, and here this is the height of the step. Okay, so in the question it is mentioned it is v naught, and here the particle is incidenting with this energy. So it's clear in this region, second region, energy is less than v naught, but here the potential is 0. That means the particle is a free particle. Here x equal to 0. Okay, so he's asking the space part of wave function for x greater than 0. So this is the x greater than 0 region. So if you consider x greater than 0 region, so here the condition is energy is less than v naught. Energy is less than v naught. That's why solution psi is exponential. But this is a right side. So that means as x tends to plus infinity, this is the right side. So we know what is the right side valid wave function, that is a decay function, a e raised to minus kx. This will be the form. So the answer is 2. So here they have given potential regions. Let us say this is a region 1 and this is a region 2 and this is a region 3 and this is a 4, of course. So here we have infinite potential, so the particle cannot cross this barrier. Okay, so it should, the wave function should end at this point. Okay, fine, that means x is equal to b. So here it is x equal to b. Now if you see the left side of x equal to 0, here nothing is given potential, so that we can take this potential is 0. If the potential is 0, here the particle is a free particle. First let us find the nature of the potential. Here it's a free particle, potential is 0. And the second region, this is the barrier. This barrier, what is the height of the barrier? This is a v naught given. But the condition is asking the particle energy is E less than V naught. So that's why we are sending this is the energy of the particle, okay, which is less than the V naught. Okay, right. So it is crossing the barrier with energy less than V naught. That's why in this region we have E less than V naught. That's why the solution is exponential, that to decay. And here the solution is sinusoidal. Here the solution is sinusoidal. because it's a free particle. And after that again here the potential is a 0, so that's why we can say the solution is again a sinusoidal. And of course here the wave function is a 0. So by taking all these things into consideration, we can say this is not at all the answer. Third one is not the answer. The reason is here in the third region, that means A to B, we have sinusoidal, but there is no sinusoidal, so that's why third one is not the answer. And the first one and the second one and fourth one is having sinusoidal, but fourth one is not the answer. The reason is, whenever you are representing the wave function, probability or wave function, whatever it is, we have to represent the nodes. So nodes, that means touching the x-axis here. So if it is not touching the x-axis, the amplitude is not equal to, we can't take it as a 0. So that's why that graph wave function must touch the x-axis. So your option will be either 1 or 2. See, first region sinusoidal, sinusoidal. Next, third region sinusoidal and sinusoidal. So in between 0 to A, we have the exponential decay. If you observe carefully, it seems to be exponential decay, and this is also seems to be exponential decay. Now carefully observe this point here. So here we have some sudden change or some sharp edge, and here some smooth change. So that's why this is not at all valid, and first one is the valid wave function, I mean probability distribution. Here they have given some wave functions, and they are asking which of the following represent the proper wave function. If you see the first one, so here we have a sudden change at this point. So that's why we can say in this first one, dou psi by dou x is discontinuous. But we know the first derivative of the wave function must be continuous, that means smoothly varying. And the second also the same thing, there is a sudden change at this point, the same reason, dou psi by dou x is a discontinuous here also. Okay, and if you see the third one, it's a continuous, smoothly varying, that's why psi is continuous, dou psi by dou x is continuous, and dou psi it's a single value, so all the properties are satisfying here. And if you see the fourth one, the same logic, at this point what's happening, there is a sudden change, that's why dou psi by dou x is discontinuous in this also. So the answer is the third one. In this question, so they have given some potential wells. The first one, that is A, this side we are having 2 V naught, and this is a V naught. Okay, and here for B this is a infinite height, and here the potential is a V naught. For C, both the sides it is infinite. So finally the conclusion is, if you consider the particle wave function in the C, it should exist between this 0 to A only, and that too he is asking the ground state energies. So the minimum possible case we have to take. Okay, and if you consider this B, this side infinite height, that's why here is a node, but here there is a possibility of coming out because of a finite potential height. That's why your wave function will be like this. And next, if you see the first one A, on both the sides we have finite potential, that's why the particle can cross the barrier, so this will be the possible case. And if you see here, this is the lambda C, and this is a lambda B, and this is a lambda A. This lambda C is less than lambda B, less than lambda A, that means lambda A is more. So we can say lambda A is greater than lambda B is greater than lambda C. So finally we can say energy of E is less than energy of B is less than energy of C. So then the answer is A. Now here they have given some wave functions, and they are asking which of the following is the valid wave function for the bound state. Remember, it's a bound state. So bound state means definitely it must tend to 0. Okay, so let us eliminate the wrong one. So this is going to infinite. This is not at all a valid wave function, because the wave function must be finite. So this is invalid, this one. And here this is also invalid because it is a discontinuous. Psi is a discontinuous. So that's why this is also invalid. Now come to this 1 and 2. 1 and 2. So 1 there is no issue because it is coming to 0 here. Everything is satisfied. Then what's wrong with this second one? If you see the second one, it's sinusoidally varying, but actually it is not coming to 0. So that means it must tends to 0 like this, like this, like this. So but it is not like this. That's why the second also wrong. So the answer is 1. So here they have given some options wave functions and asking what is the acceptable wave function in the range minus infinity to plus infinity. So this is the most important reason, minus infinity to plus infinity. Okay, so here we are finding the valid wave function from minus infinity to plus infinity. So the first one is psi of x equal to a tan x. This is not a valid wave function, not a valid wave function. The reason is of its discontinuous, discontinuity, and its sudden changes. And if you see the second one, that is psi equal to b cos kx. Remember, psi equal to a sin x or psi equal to b cos x, whatever it is. Sine and cos are valid wave functions only in a particular given region. That means, let me explain. These are valid only in a given region, not minus infinity to plus infinity. The reason is, whenever you have taken a 1D box, okay, so you will take the boundaries as 0 to a, or sometimes we will take minus infinity to plus infinity, minus a to plus a, something like this. So for this only we are having the solution sine or cos something. So sine and cos are valid only for a given boundaries or given region, not for minus infinity to plus infinity. Next, third one, this is the psi equal to c e raised to minus d by x square. First let us draw the wave function. So this is x-axis and this is the psi. Now carefully observe how to draw the wave function. First put x is equal to 0. If I substitute x equal to 0 here, e raised to minus d by 0, that is e raised to minus infinity. E raised to minus infinity is what? 0. Okay. Next, if I check the nature of the wave function as x tends to infinity, then means if I substitute x is equal to infinity here, so if I substitute x equal to infinity there, this is something by infinity 0, e raised to minus 0 is 1. So what is happening here? From 0 the function is increasing, and for larger values of x it's become constant, that is c, constant. And the same as in the negative region also. The reason is very simple. Here we have x square. So if you substitute positive values or negative values, the result won't change. The reason is here we have x square. So now I hope you got it. So it is going to infinity. So it is not converging. So that's why it's not at all a valid wave function. The reason is not converging. Or you can say it's not a it's not a finite wave function. Next, fourth one, if you see the fourth one, so this is a psi of x equal to e, some constant x, e raised to minus f x square. This is actually later we will study. This is nothing but a first excited state of linear harmonic oscillator. First excited state of linear harmonic oscillator. The wave function will be like this. See, here we have a node somewhere, and this is a tending to 0 and this is also tending to 0. So all the points are valid. That's why the valid wave function is a 4. So here they have given the time independent Schrodinger equation of a system represent the conservation of water. So if you see time independent Schrodinger equation, that is H psi equal to E psi, where H is minus H cross square by 2m del square plus potential energy V. So psi equal to E psi. So what is this? This is nothing but the total energy of the particle. So this is the total energy operator or total energy operator of the system. So the time independent Schrodinger equation represent total binding energy, no, total potential energy, no, total kinetic energy, no. This is the total energy of the system. So answer is 4. So here they have given some wave functions and asking which of the following is the bound state wave function in the 3 dimension. They are asking in the 3 dimension. Okay, so fine. First is take the first one, that is a psi equal to a e raised to minus alpha 1 r plus b e raised to plus alpha 2 r. See, actually this is a valid only in the positive side, that means r tends to plus infinity, or right side, something like this, and this is a valid only in the left side of the region, left side of the origin. So both the things, it's not possible to stay in consist in a one wave function. That's why this is not a valid one. And second one, this is e raised to minus of x square plus y square plus z square by alpha square. So this can be written as, this is a psi is equal to e raised to x square plus y square plus z square is nothing but r square by alpha square. So if you take r tends to plus r minus infinity, your psi is becoming finite, that is tends to 0. So there is no issue with the 2. Let us see the other things also. Third one, e raised to ik r by r. Remember, this is the spherical wave front. This is a spherical wave front or spherical wave. So which is undefined at r is equal to 0. So that's why we can't take this also. And a fourth one, this is a psi equal to e raised to minus of x square plus y square minus z square by alpha square. Unfortunately, we can't express this as a r square. So that's why this is also not a valid wave function. So the final answer is this is second one. So here they have given a wave function, that is a psi equal to a e raised to minus mod x. Okay, a is a constant. This implies that the potential A, option A, differentiable everywhere, He's talking about the potential, be careful, he's not talking about the wave function, he's talking about the potential. So differentiable everywhere and continuous everywhere but not differentiable, and has a discontinuity at x equal to 0, has a discontinuity at x equal to plus or minus 1, but a differentiable everywhere else. Actually this will give you the if you split this, psi is equal to a e raised to minus x. This is the if mod x is equal to minus x, then it will be plus. This is the negative region, that means x less than 0 solution, and this is the psi 2, the a e raised to, in the positive region it is a minus x. So this is the solution in the positive region and this is the solution in the negative region. Actually this is the solution of the potential, Dirac delta potential. So what is the form of a delta Dirac potential? The delta Dirac potential will be like this. So just a spike. Sorry. But actually this solution is attractive potential, so that's why we have to take like this. So this is the potential V of x. Actually this is a minus some constant alpha delta of x. This is a Dirac delta function. So what are the properties of this Dirac delta potential? It's a continuous everywhere, but it is not a differentiable at x equal to 0, because if you see at x equal to 0 a sudden change is there. Whenever you have a sudden change at a particular point, then what is a discontinuous? First derivative is discontinuous. The potential is continuous everywhere, but it is not a differentiable. The reason is dou psi by dou x is discontinuous. That's it. So answer is 2. 2 is the answer. So here they have given wave functions asking which of the following is the valid wave function. And if you see this first one, if you draw a line parallel to y-axis, it is cutting the graph at more than one point. That's why it is not a single valued. So that's why this is not a valid wave function. And if you see here, there is a sudden change at this point. Okay, so that's why first derivative is a discontinuous. Dou psi by dou x is a discontinuous. And here, of course, if you draw a vertical line like this and it is cutting the graph at more than one point, that's why it's not a single valued. This is not a single valued, as well as there is a sudden changes. That's why we can say dou psi by dou x, first derivative dou psi by dou x is not continuous or discontinuous. So it's not a differentiable function. This is not a differentiable function. So here, although the amplitude is decreasing, this is a sinusoidal behavior only, but a damped. So this indicates a damped oscillations, something like this. That means amplitude is decreasing. That's why it's a valid one. So answer is 2. In this, they are asking, the potential is given. And asking which of the following is the valid wave function in the regions. That means in the first region and the second region as well as a third region. First let us find the potentials. So in this first region the potential is 0, it's a free particle. So that's why the solution is sinusoidal. And here we have some potential. So this is the potential barrier. And of course here this is the energy, but this is the potential. So we can say energy is less than V naught. So in this A to B the solution is exponential. nature. And third region, again the potential is 0. Okay, so again the solution is sinusoidal. This is also sinusoidal. But whenever the particle is passing through the barrier, so what will happen? So here we are having a sinusoidal behavior, and here also sinusoidal behavior. The only difference is here in this region the amplitude is less compared to the first region. So sinusoidal with more amplitude, sinusoidal with less amplitude, and here it indicates some decrease in this amplitude. So because this is the potential barrier, so if you observe all these conditions, I think the third option is the correct one, because here it is a sinusoidal, here it is a sinusoidal, and here it is a decaying. So amplitude is more in this region, amplitude is less in this region. So here they have given one potential, okay, and asking which of the following is the possible wave function for a bound state. Remember, bound state means bound state. So it should be, I mean, psi is tending to 0. Okay, that means converging. First identify where is this converging behavior. So here it is not tending to 0, and here is a tending to 0, tending to 0, here also tending to 0. But unfortunately this is a discontinuous. This is discontinuous, that's why it is not valid. And here we have sharp changes, sudden changes, that's why first derivative is a discontinuous, dou by dou x is a discontinuous. That's why this is also not valid. And this is not a bound system, that means it's not tending to 0, it's not converging. So that's why this is also wrong. So the answer is the second one.